Good morning guys and welcome back to Dynamics course. In this video lecture we're going to talk about curvilinear motion using normal and tangential components. So far guys, we have expressed the curvilinear motion using rectangular components, which means I have represented my position in terms of x, y, z, my velocity in terms of vx, vy, vz, my acceleration in terms of ax, ay, az in ijk plane. And what helps me in doing this is that, guys, the unit vectors I, j, k are fixed with respect to time. A vector is fixed with respect to time if its magnitude is constant and its direction is not changing. That's why I, j, k are fixed. The rectangular unit vectors are fixed. And that's why if I need to find Vx, I can directly do the derivative of x with respect to time. That's why if I need to find Ay, for example, I can do the derivative of Vy only with respect to time. So guys, in order to represent the curvilinear motion in rectangular components, I have to represent my position x, y, z, do the first derivative to find v, do the second derivative to find a, because the unit vectors I, j, k are fixed with respect to time. Now what if I need to represent my curvilinear motion using normal and tangential components? First of all, let's define the normal unit vector and the tangential unit vector. A tangential unit vector is a unit vector which means it has a magnitude of 1 that is tangent to the path. At each point, this unit vector, this tangential unit vector ut, is changing. For example, if at a certain time t prime, this particle is at this position, then my unit vector will be this one. This unit vector, guys, has always a magnitude of 1. And this means, guys, that its magnitude is not changing with respect to time. Can I say that this is a fixed unit vector? No way. Because in fact, this unit vector is changing its direction. It's not fixed. It's not a constant vector. It's changing its direction so that it is always tangent to the path of this particle. What about un? Un is a unit vector that is always directed towards the center of curvature. Like this here, this location here. It has this center of curvature. We're going to talk about the radius of curvature and the center of curvature. Un is a unit vector from this particle to the center of curvature. Now guys, ut is indicating the positive tangential direction, so it is always directed with the motion or in the direction of the particle's motion, while un is always directed towards the center of curvature, which means, guys, the direction, the positive direction and the normal direction should be towards the center of curvature. For example, this is a normal direction that is negative because it is in the opposite direction of this un. So these are by definition the normal and tangential directions as well as the normal unit vector and the tangential unit vector. Now guys, if I need to define this center of curvature, I'm going to start by defining the radius of a curvature. The radius of a curvature is defined as rho. And rho, guys, if you want to do the analogy, it is r in the circle. So if I have a circle, the radius r is the radius of curvature, right? So since this is a circle, this will be the center and this will be r. In this case, the radius of curvature is the same as the radius of this circle. So what is the radius of curvature? So in order to understand what is the radius of curvature, I'm gonna share with you this figure here. In fact, guys, the radius of a curvature is the radius of a circle that best fits the arc of this curvature. This is an imaginary circle completing this curve in order to know what is the radius of curvature. So if I take, guys, for example, this portion here called ds, and if I complete the circle, that best fits this arc here, so let's do it using shapes. For example, guys, this is an imaginary circle, but if you take a look, guys, as if this arc right here, ds, belongs to this imaginary circle. If I take the origin of the circle, O prime, and draw the radius of the circle, this will be the radius of curvature rho. And don't forget, guys, this is an imaginary circle, but it fits this arc, or this arc belongs to the circle, all right? So that's why, guys, I can say that the radius of the circle is the radius of curvature of this arc or of this curve. So guys, we're gonna talk about the equation of this radius of curvature. What matters for me now is to know what is the definition of a radius of curvature, and that the center of curvature, O prime, always lies on the concave side of the curve. So it is always lying, guys, here in the concave side of the curve. Why? Because in fact, it should be the center of this circle, all right? So this circle here will start from this concave side. You have to start from this concave side to draw the circle, all right? So you cannot put O prime or O or the center of curvature outside this concave side or outside this circle. Alright, so the radius of curvature is defined as the perpendicular distance from the curve to the center of curvature, while the center of curvature always lies on the concave side of this curve. And like, guys, the general motion that we started at the early stage of this chapter, we said that the position of the particle at any instant should be defined by S along the curve. So guys, in the rectangular component, we did not use S because in fact we are defining our position using XYZ. So S will not matter at all. Now here, guys, in the curvilinear motion using the normal and tangential components, we have to go back to using S, which is defined by the distance along the curve from a fixed reference point. All right, so I'm gonna go back to the general case. I'm gonna use S, and of course I'm gonna define V as ds over dt. So let's start. What is the equation of velocity? As we said, guys, in rectangular components, I don't have any problem in the direction of the velocity or in the unit vector ijk because they are fixed with respect to time. However, here, as I proved to you guys in this video, ut is not constant with respect to time. This is not because its magnitude is changing, this is because its direction is changing. The unit vector has always a constant magnitude that is equal to 1. But here, ut is always tangent to the path. If ut is not changing in direction, this means I have what? What type of motion? A rectilinear motion. Because in rectilinear motion, ut will have the same direction. Now here, guys, since this is a curvilinear motion, then ut, which is always tangent to the curve, should change its direction. And in this case, I have to pay attention when doing the derivative, right? So let's start by defining v. What is v? v in vector is equal to the magnitude of v, which is what? Which is ds over dt, ut. I know, guys, from the definition of ut, which is the tangential unit vector, that ut has always the direction of the particle's motion. So it is always in the same direction of v, of the velocity. And v here is the ds over dt. It's the derivative of course, of s, which is the position with respect to time. Can I say, guys, that dv over dt is only equal to dv over dt ut, or in other words, d squared s over dt squared ut? No, because in fact, guys, ut is not constant with respect to time. So there is another term here, which is v dut over dt. All right? All right? So guys, v here is the multiplication of two variables. Why are they called variables? Because ut is also a variable with respect to time. It's changing in direction. All right? So I know if I want to do the derivative of a product, I can do the derivative of the first one times the second term plus the derivative of the second terms times the first term. And this is what I did here. Now dv over dt will of course be d squared s over dt squared ut plus v times dut over dt, that I have to find what is this value. All right? What is dv over dt? This is in fact the acceleration. And this means, guys, that in curvilinear motion, using tangential and normal components, the velocity will have one term, all right? Or it will have one direction, which is ut, while the acceleration will have two parts. The first part is in the direction of ut, and this is called a tangential. And the second part has the direction of un, as we're gonna see in the next slide, and this will be called an. So the velocity has only one component in this curvilinear motion using normal and tangential components. It has only one component in the tangential direction, while the acceleration has two components. One is tangential and the second one is normal.